Hi friends, here we discuss Cauchy integral formula. The most important consequence of Cauchy-Gaussat theorem is Cauchy integral formula. Cauchy's integral formula helps us to obtain the value of an analytic function everywhere inside a simple closed curve by means of values on the boundary. We first move on to theorem. Let f be analytic everywhere inside and on a simple closed contour C, taken in the positive sense. If Z0 is any point interior to C, then f of Z0 is equal to 1 by 2 pi I integral over C fz by Z minus Z0 dz. Equation number 1. This formula is called Cauchy integral formula. Proof. Since f is analytic everywhere inside and on a simple closed contour C, in particular it is differentiable at Z0 and hence is continuous at Z0. This is our Z0, this is our C. Here x axis, y axis. Hence, corresponding to any epsilon greater than 0, however small, there exists a delta greater than 0 such that mod fz minus fz0 is less than epsilon whenever mod z minus z0 less than delta. Equation number 2. Let us now choose a positive number rho which is less than delta and is so small that the positively oriented circle mod z minus z0 is equal to rho denoted by C rho. That is, this is our rho, this is our Z0, this is our C rho. Okay. This it is denoted by this C rho, this is interior to C. Then mod fz minus fz0 less than epsilon whenever z minus z0 less than rho. Hence, for z belongs to C rho, mod z minus z0 is equal to rho, and hence by the above discussion we have mod fz minus fz0 less than epsilon dividing both sides by mod z minus z0 is equal to rho. We have mod fz minus fz0 divided by, we are dividing both sides by z minus z0, z minus z0, it is less than epsilon by rho. Equation number 3. This inequality plays an important role in the rest of the proof. Here the function fz by z minus z0 is analytic at all points within and on C except at the point z0. In particular, fz by z minus z0 is analytic in the closed region consisting of the contours C and C rho and all points between them. Hence, by the principle of deformation of paths, we can write deformation of paths we have discussed earlier. So, by using that we can write integral over C fz by z minus z0 dz, which is equal to integral over C rho fz by z minus z0 dz. This enables us to write integral over C f z by z minus z naught dz minus dz minus f z naught into integral over C rho f z minus integral over C rho dz by z minus z naught. This is equal to integral over C rho what f z minus f of z naught by z minus z naught dz. Before proceeding further, first we evaluate integral over C rho dz by z minus z naught. This is our equation number 4. Mark it as equation number 4. So, before proceeding, first we have to calculate integral over C rho dz by z minus z naught. C rho is given by z of t is equal to z naught plus rho e raised to I t, where this t varies in between 0 less than or equal to t less than or equal to 2 pi. That is integral over C rho dz by z minus z naught is equal to integral 0 to 2 pi 1 by z of t minus z 0 into z dash of t dt. So, by substituting the z of t and z dash of t here, we get that is integral 0 to 2 pi 1 by rho e raised to minus I t into rho I into e raised to I t dt, which is equal to, we can cancel and we can cancel this rho and e raised to I t. So, it becomes integral 0 to 2 pi, what remains here? It remains only I, it is I dt. So, it becomes, which is equal to 2 pi I. Hence, equation 4 becomes, therefore, our equation number 4 that becomes integral over C dz by z minus z naught dz minus, we have to substitute the value, minus 2 pi I f z 0, which is equal to, it becomes integral, it is over 0, integral over 0 f z minus f of z naught by, in the denominator we have z minus z naught into dz, equation number 5, fifth equation. Referring now to statement 3 and noting that the length of C rho, that is the length of the circle having radius rho is 2 pi rho. Now, applying the ML inequality, we obtain with the length L of C rho is 2 pi rho, that is modulus of integral over C rho dz by, no, it is f z minus, here it is f z minus f of z naught by z minus z naught into dz. It is less than epsilon by rho into 2 pi rho. So, this is equal to 2 pi epsilon. Hence, by equation 5, we can say modulus integral over C rho f z by z minus z naught d z minus 2 pi I into f z naught, it is less than 2 pi epsilon. Since the left hand side of the above inequality is a non-negative constant, that is less than an arbitrary small positive number, so it must be equal to 0. Hence, modulus integral over C rho f z by z minus z naught dz minus 2 pi I f of z naught is equal to nothing but this is a small quantity which is equal to 0. Thus, integral over C rho f z by z minus z naught dz is equal to 2 pi I f of z naught. Next, we have some examples. First example is to evaluate integral over C z square by z minus 2 dz, where the C is the unit circle, not the unit circle, it is the circle where mod z is equal to 3. Here it is given f z is equal to z square. This is our f z, it is z square, and the z square is analytic everywhere within and on the circle. Mod z is equal to 3 and z naught is equal to 2 is an interior point of mod z is equal to 3. Then by Cauchy's integral formula, integral over C this z square by z minus 2 dz is equal to 2 pi I f of, instead of z naught here we have 2, this is actually 2, f of 2 which is equal to 2 pi I. What is f of 2? We have f of z is equal to z square. So, f of 2 is 2 square. So, it becomes 8 pi I. The answer is 8 pi I. Next, integrate z square plus 1 by z square minus 1 in the counterclockwise sense around a circle of radius 1 with the center at the point. First one is z is equal to 1. Next one is at z is equal to 1 by 2. Third one is z is equal to minus 1. Fourth one is z is equal to I. So, proof of the first one, that is center at z is equal to 1. The question is to integrate over C what z square plus 1 by z square minus 1 into dz. This I can write as, this is equal to integral over C z square plus 1. Here it is a square minus b square form. So, I can write it as z plus 1 into z minus 1 into dz. If we take f z is equal to z square plus 1 by z plus 1 and z naught is equal to 1. Here z naught is 1. We have z naught is inside C and f z is analytic inside and on C. Then we can apply Cauchy's integral formula, that is integral over C z square plus 1 by z square minus dz is equal to integral over C f z by z minus 1. Here note that our f z is z square plus 1 by z plus 1. This term we are taking it as f of z. So, f of z by z minus 1 dz. So, by applying Cauchy's integral formula, it is equal to 2 pi I into f of 1. That is, our f of z is z square plus 1 by z square minus 1. No, our f of z is z square plus 1 by z plus 1. So, it becomes 2 pi I into 1 plus 1 by 1 plus 1. So, it is equal to 2 pi I itself. Okay. Next one, that is the B part. Here the center z is equal to 1 by 2. The z is equal to 1 by 2. The function is again z square plus 1 by z plus 1, is analytic everywhere inside the circle C of radius 1 with the center at the point z is equal to 1 by 2. That is, it is just like this. Center is at 1 by 2 with the radius 1. So, it is just like this. Here center 1 by 2, here we have minus 1 by 2, this is 3 by 2. If we take f z is equal to z square plus 1 by z plus 1 and z naught is equal to 1, we have z naught is inside C and f z is analytic inside and on C. Then applying Cauchy's integral formula, we get integral over C z square plus 1 by z square minus 1 dz, which is equal to integral over C f z by z minus 1 dz. Here also our f z is z square plus 1 by z plus 1. So, f z by z minus 1 dz, which is equal to, applying Cauchy's integral formula, 2 pi I into f of 1, which is equal to 2 pi I. Okay. Next, that is here C z is equal to minus 1, that is the circle with the center minus 1 and again the radius 1. C z is equal to minus 1. We take f z is equal to z square plus 1 by z minus 1 and z naught is equal to minus 1 in the Cauchy's integral formula, and the value of the integral as integral over C z square plus 1 by z square minus 1 dz, which is equal to integral over C f z by z plus 1 dz. No, it is z minus 1, z minus 1 dz into dz by z plus 1, which is equal to integral over C f z into dz by z minus minus 1. It is equal to 2 pi I into what? Minus 1 square plus 1 by minus 1 minus 1. So, on computing, it is equal to 2 pi I into f of minus 1. Which is equal to minus 2 pi I. The value is minus 2 pi I. This is the value of the integral with the center z is equal to minus 1. Next, at z is equal to I. If we take f z is equal to z square plus 1 by z square minus 1, then f z is analytic everywhere inside and on the circle mod z minus I is equal to 1. here mod z minus I is equal to 1. And hence we obtain by Cauchy-Gosat theorem that the value of the integral is 0. So, nothing to prove. Next example is, we have to evaluate integral over C z square minus 1 by 3 by z cube minus z dz, where the C is a circle mod z minus 1 by 2 is equal to 1. Oriented in the counterclockwise direction. Solution. Since z cube minus z, that is, we can write z cube minus z is equal to z into z square minus 1, which is equal to, again we can split z into z plus 1 into z minus 1. The integrand can be written as z square minus 1 by 3 by z cube minus 3 is equal to z square minus 1 by 3 by, here we can split this denominator as by z into z plus 1 into z minus 1, which being a rational function is differentiable everywhere except at z is equal to 0, z is equal to minus 1 and z is equal to 1. Hence, the function z square minus 1 by 3 by z cube minus z is analytic in every domain not containing that 3 points, that are z is equal to 0, z is equal to minus 1 and z is equal to 1. Here, the path of integration C is a circle mod z minus 1 by 2 is equal to 1, that is circle with the center 1 by 2 and a radius 1. The points z is equal to 0 and z is equal to 1 lie inside C, and the point z is equal to minus 1 lies outside C. To apply the method of partial fractions, we let, that is z square minus 1 by 3 by z cube minus z, which is equal to, we can write it as a by z plus b by z plus 1 plus c by z minus 1. Then z square minus 1 by 3 is equal to a into, here it is z square minus 1 plus b into z into z minus 1 plus c into z into z plus 1. From this we get the values of a, b, c as like this. A is equal to 1 by 3, b is equal to again 1 by 3 and also c is equal to 1 by 3. Hence, integral over c, you can write this as integral over c z square minus 1 by 3 by z cube minus z dz is equal to, of course, here we have dz, which is equal to 1 by 3 integral over c 1 by z dz, first term is 1 by z dz, plus again the value of b is 1 by 3 integral over c 1 by z plus 1 dz, plus 1 by 3 integral over c 1 by z minus 1 dz. Now, z is equal to 0 is a point within C and f of z is equal to 1 is analytic everywhere. Hence, by Cauchy integral formula, integral over C 1 by z dz is equal to integral over C dz by z minus 0. Fz by z minus 0 dz, which is equal to 2 pi I f of 0. That is f of 0 is 1. So, it becomes 2 pi I into 1. So, it is equal to 2 pi I. 1 by z plus 1 is analytic everywhere except at z is equal to where z is equal to minus 1, which is a point outside C. Hence, 1 by z plus 1 is analytic within and on C. Hence, by Cauchy-Gosat theorem, integral over C 1 by z plus 1 dz is equal to 0. So, no problem with this term. Next one is z is equal to 1 is a point within C and f of z is equal to 1 is analytic everywhere. Hence, by Cauchy integral formula, integral over C 1 by z minus 1 dz is equal to integral over C 1 by z minus 1 dz, which is equal to integral over C f z by z minus 1 dz, which is equal to using Cauchy's integral formula 2 pi I f of 1, which is equal to again value is equal to 2 pi I. Hence, altogether we have integral over C z square minus 1 by 3 into z cube minus z dz is equal to. Now, we have to substitute the values of these three integrals, which is equal to, first one we got it as 2 by 3 pi I plus second term we got it as 0. So, second term is 0 plus third term is 2 by 3 pi I. So, by adding 2 by 3 pi I and 2 by 3 pi I, we got it as 4 by 3 pi I. This is the value of this integral. Next example is integrate gz around the circle C such that mod z is equal to 3 by 2 in the clockwise direction, where gz is given as tan z by z square minus 1. Here C is such that mod z is equal to 3 by 2. The given contour is a circle with a center, origin and a radius 3 by 2. Let f z is equal to tan z. We know that tan z is analytic everywhere, but except at z is equal to plus or minus pi by 2, plus or minus 3 pi by 2, etc. But all these points lie outside the given contour, that is mod z is equal to 3 by 2. Hence, our f z, that is tan z, is analytic within and on C. The function 1 by z square minus 1, in the denominator it is z square minus 1, this we can write as 1 by z plus 1 into z minus 1, being a rational fraction is differentiable everywhere except at z is equal to 1 and z is equal to minus 1. Both the points, that is z is equal to 1 and z is equal to minus 1, lie inside our given contour C. Now, we can write 1 by z square minus 1 as in case of previous example. It is written as a by z plus 1 plus b by z minus 1, or I am taking a by z minus 1 and b by z plus 1. So, it gives a is equal to 1 by 2 and b is equal to minus 1 by 2. Hence, 1 by z square minus 1 is equal to 1 by 2 into 1 by z minus 1 minus 1 by z plus 1. Since C is oriented in the clockwise direction, we have integral over C gz dz. Integral over C gz dz is equal to integral over C f z by z square minus 1 dz. Remember, our f z is tan z, which is equal to 1 by 2, this is not z, this is actually 2, 1 by 2 integral over c f z by, first one is z minus 1 dz minus, here 1 by 2 is, I am taking this 1 by 2 as common, integral over c f z by z plus 1 dz, which is equal to, now we have to substitute the values, it is 1 by 2 into minus 2 pi I f of 1 minus, here 2 pi I f of minus 1. Now, minus 2 pi I f of minus 1 by Cauchy integral formula. So, this is equal to, which is equal to minus pi I tan 1 minus tan minus 1. You have to find what is f of 1 and f of minus 1. Our f of 1 is tan z. So, f of z is tan z. So, f of 1 is tan 1 and f of minus 1 is tan minus 1. So, it becomes, which is equal to minus 2 pi I tan 1. So, these are the examples. Next, we have an extension of the Cauchy integral formula. It is a theorem. If f z is analytic in a domain D, then it has derivatives of all order in D, which are then also analytic functions in D. The values of these derivatives at a point z naught in D are given by the formulas f dash of z naught, which is equal to 1 by 2 pi I integral over c f z by z minus z naught whole square dz. It is our next equation, I think it is equation number 6, and f double dash z naught, f double dash z naught is equal to 2 factorial by 2 pi I integral over c f z by z minus z naught whole cube dz. Equation number 7. That is, in general, f n z naught is equal to n factorial by 2 pi I integral over c f z by z minus z naught whole raised to n plus 1 dz. Here for the second derivative it is whole cube. So, for the nth one it is n plus 1 dz, equation number 8. Here C is any simple closed path in D which encloses z naught and whose full interior belongs to D, and the curve C is oriented in the counterclockwise sense. Remark: note that with the argument f of 0 z naught, that is f0 z naught, which is equal to f of z naught, and 0 factorial is considered to be 1. The formula f n z naught is equal to n factorial by 2 pi I integral over c f z by z minus z naught n plus 1 dz is also valid when what n is equal to 0, as it then becomes the Cauchy integral formula. That is, f of z naught is equal to 1 by 2 pi I integral over c f z by z minus 0 dz. This together with this equation, this 8, gives f n z naught is equal to n factorial by 2 pi I integral over c f z by z minus z naught raised to n plus 1 dz, where n varies from 0, 1, 2, 3 etc. Equation number 4. Here equation number 9, n varies from 0, 1, 2, 3 etc. Here it is true for n is equal to 0 also. Given f set is analytic in a domain D and Z0 belongs to D. Hence, f set is analytic at Z0 and f dash Z0 is equal to f dash Z0, which is equal to limit delta Z tending to 0 f of Z0 plus delta Z minus f of Z divided by delta Z. Let C be any simple closed contour in D enclosing Z0 and oriented in the counterclockwise direction. Let D denote the smallest distance from Z0 to the point Z on C. Choose delta Z0 sufficiently small so that 0 less than mod delta Z0 less than D, so that Z0 plus delta Z0 lie within C. Now, look at this figure. Then, by Cauchy integral formula, f of Z0, that is f of Z0 is equal to, by integral formula what we can write, it is equal to 1 by 2 pi I, yes, integral over C f of Z by Z minus Z0 dz, and f of Z0 plus delta Z0, which is equal to 1 by 2 pi I integral over C f Z by, instead of Z0 here we have Z0 plus delta Z0. So, it become f Z by Z minus Z plus delta Z0 dz. Therefore, we can write f of Z0 plus delta Z0 minus f of Z0 by delta Z0 as, this can be written as, which is equal to 1 by delta Z0 1 by 2 pi I, that is f of Z plus delta Z0. We are substituting the value here 1 by 2 pi I integral over C f Z by Z minus Z plus delta Z0. No, it is Z0. Here also it is Z0. Z0 plus Z0 plus delta Z0 dz minus, that is our first term, minus, what is our f of Z0? It is 1 by 2 pi I integral over C f Z by Z minus Z0 dz. 1 by delta Z0 is a common term, I can take it outside. It is equal to which is equal to 1 by delta Z0 1 by 2 pi is a common term into 1 by 2 pi I integral over C, what remains 1 by Z minus Z0 plus delta Z0 minus 1 by Z minus Z0, this remains into f Z dz. This is equal to 1 by 2 pi I, this is 1 by 2 pi I integral over C f Z by Z minus z naught minus delta z naught into z minus z naught dz. Hence, f of z naught plus delta z naught minus f of z naught by delta z naught minus 1 by 2 pi I integral over c f z by z minus z naught whole square dz is equal to what? 1 by 2 pi I integral over c f z by z minus z naught minus delta z naught into z minus z naught dz minus the other term 1 by 2 pi I integral over c f z by z minus z naught whole square dz, which is equal to, that is equal to 1 by 2 pi I integral over c delta z naught dz by z minus z naught minus delta z naught into z minus z naught square. Here we have f z also, f z dz. Equation number 10. Now, let m be the maximum value of mod f of z on C. Since mod z minus z naught is greater than or equal to d and mod delta z naught is less than d, we get mod z minus z naught minus delta z naught, which is equal to, which we can write as mod z minus z naught minus delta z naught. It is greater than or equal to mod z minus z naught minus mod delta z naught, which is greater than or equal to d minus mod delta z naught. It is again greater than 0. Hence, hence delta z naught f z divided by this one mod z minus z naught minus delta z naught into z minus z naught whole square, it is less than or equal to mod delta z naught into m by d minus mod delta z naught into d square. Hence, if L is the length of the contour C, by applying our ML inequality, we get modulus of integral over C delta z naught f z by z minus z naught minus delta z naught into z minus z naught whole square dz. It is less than or equal to mod delta z naught into ML divided by, in the denominator we have, it is d minus mod delta z naught into d square. Since right hand side of the above inequality tends to 0 as when delta z naught tends to 0, it follows that limit delta z naught tending to 0 here. Here limit delta z naught tending to 0 integral over c delta z naught f z by z minus z naught minus delta z naught into z minus z naught whole square dz is equal to 0. Equation number 11. From 5 and 6 equation, we get limit delta z naught tending to 0, f of z naught plus delta z naught minus f of z naught by delta z naught minus 1 by 2 pi I integral over C f z by z minus z naught whole square dz is equal to 0. Hence, our f dash z naught is equal to f dash z naught is equal to limit delta z naught tending to 0 f of z naught plus delta z naught minus f of z naught divided by delta z naught is equal to what we can write, which is equal to 1 by 2 pi I integral over C f z by z minus z naught whole square dz. Hence, the result is true for n is equal to 1. Now, let us assume that the theorem is true for n is equal to m. That is, f has a derivative of the order m in D and for all z naught in D. So, we can write fm z naught, that is fm z naught is equal to, we are supposing this is true, the result is true for n is equal to m also. So, fm z naught is equal to m factorial by 2 pi I integral over C f z by z minus z naught whole raised to m plus 1 dz. Equation number 12. Choosing delta z naught sufficiently small so that z plus z naught lie within C. Then using equation number 12, we obtain fm z naught plus delta z naught minus f of z fm z naught divided by delta z naught, which is equal to 1 by delta z naught into, that is the first term is m factorial by 2 pi I integral over C f z by z minus, our z naught is z naught plus delta z naught. So, z minus z naught minus delta z naught dz whole raised to, here it is m plus 1 whole raised to m plus 1 dz minus, next one is m factorial by 2 pi I integral over C f z by z minus z naught whole raised to m plus 1 dz. This is our fm z naught plus delta z naught minus fm z naught, which is equal to m factorial by 2 pi I delta z naught integral over C 1 by z minus z naught plus delta z naught whole raised to m plus 1 into 1 by z minus z naught whole raised to n plus 1 f z dz. That is, we are taking the common terms together. So, this is equal to m factorial by 2 pi I delta z naught integral over C 1 by z minus z naught whole raised to m plus 1 this is a common term, I am taking it outside, not outside this integral, it is just outside this bracket, that is 1 by z minus z naught raised to m plus 1 into 1 minus delta z naught by, the remaining terms are delta z naught by z minus z naught whole raised to minus m plus 1. Minus 1. This minus m plus 1 is for this term, that is 1 minus delta z naught by z minus z naught and here we have minus 1 again into f z d z, which is equal to m factorial by 2 pi I delta z naught integral over c f z by z minus z naught m plus 1 into 1 plus m plus 1 delta z naught by z minus z naught plus m plus 1 into m plus 2 by 2 factorial into delta z naught whole square by z minus z naught whole square plus etc. Last term is minus 1, not the last term, actually minus 1 is this one, minus 1 dz. It is actually binomial expansion, that is a binomial expansion for rational index n. It is given as 1 plus x whole raised to n is equal to 1 plus n by 1 x plus n into n minus 1 by 1 into 2 into x square plus etc. So, this is equal to, it is equal to m factorial by 2 pi I delta z naught integral over c m plus 1 f z delta z naught by z minus z naught whole raised to m plus 2 into 1 plus m plus 2 by 2 factorial into delta z naught by z minus z naught plus etc. dz, that is which is equal to m plus 1 factorial by 2 pi I into integral over c f z by z minus z naught raised to m plus 2. In the bracket we have 1 plus into 1 plus m plus 2 by 2 factorial into delta z naught by z minus z naught plus etc. dz. Hence, limit delta z naught tending to 0 fm z naught plus delta z naught minus fm z naught by delta z naught exist, and limit delta z naught tending to 0 fm z naught plus delta z naught minus fm z naught by delta z naught is equal to m plus 1 factorial by 2 pi I integral over c f z by z minus z naught raised to m plus 2 dz. Thus, if f has derivative of order m at z is equal to z naught, it has a derivative of order m plus 1 at z is equal to z naught, and f m plus 1 z naught is equal to limit delta z naught tending to 0 fm z naught plus delta z naught minus fm z naught divided by delta z naught, which is equal to m plus 1 factorial by 2 pi I integral over c f z by z minus z naught whole raised to m plus 2 dz. Hence, by induction f has derivative of all orders at a z naught and for n is equal to 1, 2, 3 etc. That is fn z naught is equal to n factorial by 2 pi I integral over c f z by z minus z naught raised to n plus 1 dz. Since z naught is an arbitrary point of D, it follows that f has derivative of all orders in D. Some examples. First one is to integrate the function z raised to 4 minus 3z square plus 6 divided by z plus I whole cube. In the counterclockwise sense around the circle, here it is mod z is equal to 3 by 2. Let C be the path of integration, mod z is equal to 3 by 2. Then C is a circle with centers origin and a radius, this one 3 by 2, oriented in the counterclockwise direction. Also let Fz is equal to, our Fz is equal to z raised to 4 minus 3z square plus 6. Then Fz being a polynomial, it is analytic everywhere and hence analytic within and on C, and z is equal to minus I is a point within C. Hence integral over C z raised to 4 minus 3z square plus 6 by z plus I whole cube dz, which is equal to integral over C Fz by, our Fz is z raised to 4 minus 3z square plus 6, Fz by z minus minus I, z minus minus I whole cube dz. Here it is actually z plus I am taking minus of minus, which is equal to 2 pi I by 2 factorial into f double dash of minus I using 8 with n is equal to 2, which is equal to pi I d square by dz square, it is actually f double dash. So, it is d square by dz square z raised to 4, our f of z is z raised to 4 minus 3z square plus 6, that is z is equal to minus 1, which is equal to pi I 12 z square minus 6, that is z is equal to minus 1. So, it is equal to minus, the answer is minus 18 pi I. Here d square by dz square means we have to differentiate this twice and applying z is equal to minus 1. So, it becomes minus 18 pi I. Next example, it is to evaluate integral over C z plus 1 by z square dz, where C is any path enclosing the origin. That is integral over C z plus 1 by z square dz. In the formula, f dash z naught is equal to 1 by 2 pi I integral over C f z by z minus z naught whole square dz. If we take f z is equal to z plus 1, that is f z is equal to z plus 1 and z naught is equal to 0, then integral over C, then it becomes integral over C z plus 1 by z square dz is equal to 2 pi I by 1 factorial into f dash of 0. This is equal to 2 pi I, 1 factorial is 1 itself, f dash 0 means first derivative, that is d by dz of, what is our f of z? It is z plus 1. We have to differentiate this one once. So, this is equal to, and at the point z is equal to 0. So, it becomes 2 pi I into 1, that is z is equal to 0, need not to apply z is equal to 0 because differentiating this we get it is a constant. So, the value is equal to 2 pi I. So, here we have discussed a very important theorem, that is Cauchy integral formula, and we have done so many examples regarding that one, and also we have another important theorem, that is the extension of this integral formula. and we have gone through so many examples also. Hope you enjoy the session. See you next time. Till then, take care.